So we're going to finish up chapter 4 by looking at what are called radical functions. So these are different examples of radical functions. Okay, we have a square root. Over here we have a cube root function plus something else, so that makes it a little more complicated. Most of the radical functions that we graph are going to look more like the first one. All right, it's going to be something like that. We're usually not going to add a variable on the end. We might add a constant on the end. And from transformations, you should know what adding or subtracting a number on the end would do. So we will talk about transformations as well. Okay, but they're going to be exactly the same as what we've always done. So any expression of the form nth root of a, okay, where the n is an integer greater than 1, is called a radical. This n is called the index, and it tells you what kind of root you're taking. If you don't put an index, we always assume it's a 2. So when you write a square root, technically you could do this. We usually don't, but you could. And the index always has to be a positive integer. Okay, there's no such thing as a negative third root. We don't do that. All right, there's also really, when we're talking about radical functions, we don't take a 1.3 root. Okay. So n is called the index, and the thing that you put under the radical symbol is called the radicand. So in this case, a is your radicand, n is your index. And then the symbol itself, that's called the radical sign. Okay, so on the calculator, we've definitely done, I think, square roots before. Just a reminder how you can do roots. There is a button for cube root. Okay, if you go to math, and you go to number, actually no, you don't even have to go to number. Just math 5, that's how you can do a generic root, and math 4 is how you can do a cube root. Right? So if you wanted to type in like a 5th root, you have to type in the index first, then math, option 5, and notice it turned what I typed into an index. Now I can put in a number and get an answer. So if you want to do a root other than square root or cube root, you type the index in first, and then you math 5. Okay, as I said, if there is no index, we always assume it's a 2, meaning we're doing a square root. And we can take anything that's written as a radical, and we can rewrite it differently without the radical. We can rewrite it with a fractional exponent. Does anybody remember what power is the same as taking a square root? Caleb?
The opposite or the same as?
So I'm looking for something I could type in, like if I did square root of 9, I would get 3. I could also raise 9 to what power and get 3?
1/2.
Yep, 1/2. So if you had something like this, you can rewrite it with a fractional exponent. It's basically 1 over the index. So what do you think a cube root would be? This would be x squared minus 1 to the what power? Yep.
1/3.
The 1/3. You might be like, well, why do we bother doing that? And we would do it in a case like this. This is x to the 4th, and that would be raised to what power? We're doing a 5th root. Michael?
1/5.
1/5. Now you have a power to a power. X to the 4th to the 1/5. What's the rule when you have a power raised to another power? What do you do with your powers? You multiply them. So what's 4 times 1/5? 4/5. Right. So if we have something like that, we can simplify it to x to the 4/5. Any questions on that? And as we go through roots, we're going to break them down into really even and odd. There's a big difference between the two. Right? The first one here is an even root, and the last two are odd roots. Odd roots have a very similar look to them, and so do even roots. All right, so if they ask us to solve for what's called the principal root in an equation, what they're asking for is one answer. For example, when you take the square root of 9, I always remind you that if it just says, what's the square root of 9? Like in a question like this, you say, how do you solve it? Well, you take the square root of both sides. There are two answers. One of those answers is the principal root. The other one doesn't really have anything, just the other answer. So I show you guys an example of the second one first. So if you're dealing with an even root, this is the second one. First of all, what you're taking the root of has to be positive. If it's not, we're going to be dealing with imaginaries, and we don't want to deal with that. Okay? So if you're dealing with an even root, and the radicand is greater than or equal to 0, it can equal 0, that's fine. You find the non-negative answer. Okay, so in other words, if I said find the principal square root of 16, the answer I'm looking for is 4. If I said to find the principal square root of 25, the answer I'm looking for is 5. Basically just solving this equation. Let's see. I'm looking for you to tell me the answer to that equation that is not negative. Could be 0, but I don't want the negative answer. I want the positive answer, or 0. Now, if n is odd, we're basically just solving that, and we can solve it for anything. Right? Cube roots, you can do them if they're positive or negative. Let's say I said for you to find the cube root of 8. That means you're solving this equation. Well, the way you'd solve it is you take the cube root of both sides. You get x equals cube root of 8. And I'm just looking for what times what is 8. In this case, it would be 2. If that was x cubed equals negative 8, just as easy to solve. The answer would be negative 2. So when you're dealing with odd roots, the answer can come out positive or negative. When we're dealing with even roots, and they're asking us to find the principal root, I always want the non-negative answer. Any questions on that? And if you remember, there are two other answers when we do cube roots. Like one answer to this is 2, but the other two answers are imaginary. So we're not dealing with imaginary answers at all. Just real answers. Okay? Just reals. Yep.
In this case, like the cube root of negative 8 would be negative 2. Can you do that? Like write it out since it's like a negative inside of a root, but it's a cube root?
Yeah, you can do that. Can I? What do you mean? Do you want me to write it? Or
No, I'm just
you're just
saying-
asking, can you do it?
Yeah.
Yeah, you can do it because the cube root of negative 8 means what times what is negative 8. Negative 2 times negative 2 times negative 2 is negative 8. And that works fine because it's a negative times a negative times a negative, which gives you a negative. Yep. So dealing with odd roots, your answer could be positive or negative. Dealing with even roots, you're only looking for the positive answer. With principal roots. Yes?
I think what she was trying to say is that, like, in the past you said in square roots, we can't have, like, negative numbers.
Not without it
it's
being imaginary. Correct.
So, but we can put negative numbers in cube roots.
Oh yeah,
Alright.
that's fine. Yep. You could do negative numbers in any odd root. Third roots, fifth roots, seventh roots. There's no, even you can do positive or negative numbers with odd roots. No problem. Even roots, you've got to stick to positives. You have to have this condition met under the radicand symbol. Okay, so now let's look at what happens when we take a square root. When we take, let's start with 4. When we take the square root of 4, what happens? It gets smaller, right? We get 2. How about if we take the square root of, well, 18? I'll just have to type it in and see. The square root of 18 gives me 4.24. What happened? Smaller. So it looks like it's getting smaller. How about the square root of 1?
Same.
Okay, so that one stayed the same. How about the square root of 1/2?
Larger.
It gets larger. What is it? You'd have to probably do it on your calculator.
107,
If you do it on your calculator, it's 0.71. Is that what it rounds to?
Yep.
So it does. It gets a little larger. And the square root of 0.2, I don't know what that is, but it will get a little larger. 0.45. Yep. So, what do you think the condition here is going to be that defines whether the square root gets larger or smaller when you do it? Depends if your number is greater than 1 or less than 1. Number greater than 1 and you take a square root, it will get smaller. A number less than 1 when you take a square root gets larger.
But it's gotta be bigger than 0. It can't be negative, right?
Correct. When we're talking about square roots, it still has to be bigger than 0. Yeah. So the smallest you could get is approaching 0, but never reaching. It can be 0, but it can't be negative. Yeah. So let's graph a few of these and see what happens. We're going to compare a square root to a 4th root to a 6th root. Okay, and see what they look like. Okay, I'll do zoom 6. We might need to zoom out or change our window a little to see what's happening. And I'm going to put it on the screen and make it a little bigger. All right, so I think you can pretty clearly see the blue is I just color code this. That was the blue, this was the red, and this one was the black. So when we are above 1, the square root is the highest, then the 4th root, then the 6th root. But let's see what's happening right around 1. So what I'm going to do is I'm going to set my window to just focus on this section right there. So let's go 0 to 2 on both. 0 to 2 and 0 to 2. So there's your square root. There's your 4th root. And here's your 6th root.
That's interesting.
So if you notice what happens, at 1 they're all the same. The square root of 1, the 4th root of 1, and the 6th root of 1 is all 1. But which one is on top switches at 1. When you go beyond 1, square roots are always higher than 4th roots, which are always higher than 6th roots. When you're before 1, the 6th root is the highest, then the 4th root, and the square root is the lowest. So we're just going to kind of summarize what's happening there. So there are 2 points that are common to all roots with even indices, assuming you don't do any transformations. All even roots will go through the origin, and all even roots will go through the point 1, 1. And you can see that here and here. Okay, so that is a point common to all of them. And from the bigger picture, when we were zoomed out, you could see the domain and the range. The domain is all numbers from 0 to infinity, and the range is all numbers from 0 to infinity. In other words, it pretty much stays in quadrant 1. It never goes in quadrants 2, 3, or 4. And technically 0, 0 is right on the origin. That's not in a quadrant, but that's the only point for an even root with no transformations that's not in a quadrant. Every other point is in quadrant 1. And when you're dealing with values between 0 and 1 for x, okay, so in other words, when you're dealing with what you can see in this section here, the square root is smaller than the 4th root, which is smaller than the 6th root. Now, when you switch that and start to look at values that are greater than 1, everything switches. For values greater than 1, the square root will be on top of the 4th root, which is on top of the 6th root. And that pretty much summarizes kind of the behavior of even roots. Now we're going to take a look at some, we're going to do odd roots next. Yep, we're going to do odd roots, and I'm just going to compare a 3rd root and a 5th root. You could throw in a 7th root, but we'll just compare 3rd root and 5th root. Alright, so let's clear that. And I can just change that to a 3 and that to a 5. Okay. Now, what did we say for odd roots? What kind of numbers are you allowed to take the odd root of? Yep.
Negative and positive.
Negatives and positives and 0. So this graph is going to go both directions, left and right. Okay, not just right. So let me just color code it. 3rd root is red, 5th root is black. So that's the 3rd root, 5th root, and let's do a zoom 6. Okay, so there's your 3rd root. So you notice that odd roots have generally kind of like an S-shaped pattern. A little different. And I definitely think we need to zoom in and kind of see what's happening. I'll put it here, but still, even if I make it bigger, you can't really see. I think what you can see is, at one point the black one is below, and at another point it's above. Okay, that you can see. But there is more happening kind of in this area. So let's zoom in -2 to 2 on everything and see if we can tell what's happening. Let's set our window. -2 to 2. So this is going to zoom us in 5 times as much. Okay, so here's our cube root. It's going to get kind of steep in the middle, so it almost looks like it disconnects. It doesn't. Alright, I think we can definitely see what's happening now. Let's take that, put that there. So does anybody see a coordinate that looks like it's in common with both of those? Nick?
0, 0.
Yep, 0, 0 is 1. Anything else? Julie?
1, 1.
1, 1, yeah. So we got this one, and yeah, go ahead, John. -1, -1. So those are 3 points that are common to all odd roots, assuming you don't do any transformations. Now it gets a little bit more complicated to explain which graph is on top of what. It kind of depends where you are. And there's different kind of sections you can be in. You kind of think of this as, oh, that doesn't work. Kind of think of this as 4 different sections. You have the section where you are less than -1. Then you have the section between -1 and 0. You have a section between 0 and 1. And then you have more than 1. If you are, let's see, between, for odd roots, if you are between -1 and 0, or if you are more than 1. Let's go. Which one was the black one? So the black one was, that was my 5th root. So between -1 and 0 and more than 1, the higher the index on the root, the lower its position when you're comparing it to something else. If you are smaller than -1 or between 0 and 1, the higher the index of your root, the higher its position compared to other graphs. Okay? So let's just summarize that. Well, first of all, domain and range is -infinity to infinity. We said that. It's going to go both directions. It goes up and down forever. And if you are in the less than -1 zone or the 0 to 1 zone, higher index will always be on top of a lower index. Look at the 0 to -1 zone. Okay. And let's look at this one and compare it. So in this case, this is saying, let's look at the greater than 1. In the greater than 1 zone, the cube root should be on top of the 5th root. Let's go back and check. In the greater than 1 zone, the cube root should be on top of the 5th root. And as long as the cube root is red, which it is, we're good. All right, so the behavior kind of switches a couple times here. A little bit more complicated than an even root. But questions on what I have right here. And this pattern continues. You know, you could do a fifth root will be below a 7th root in these two zones. You can keep continuing that pattern. Okay, everybody have that? All right. So, transformations. This is similar to the transformations we've done on everything else all year. So I'm not going to write everything down in detail, but I have an example of the A, the B, the C, and the D. And if you want to write it, you can. I'll say it. But let's start with the A. That's inside my function. What happens if you add or subtract inside your function? What does that cause your graph to do? John?
Causes it to shift up or down.
No, not up or down. Nick?
Horizontally?
That's a horizontal shift. Plus would move it which way? To the left, and minus would move it to the right. Okay, so A is your horizontal shift. How about B? John?
Vertical stretch.
No, all the horizontal stuff is always inside the function.
Horizontal stretch, sorry.
Yep,
Yeah.
so B is a horizontal stretch. And remember, just like A, it's backwards. So if you put like a 2 for B, that's actually going to compress it by 2, which is still considered, you could think of that, I guess, as a horizontal stretch of 1/2. Okay. If you put in a number like 6 for B, that's a horizontal stretch of 1/6. So you have to be careful when we talk about B. If you put in a number like 2, or actually, if you already did that one, let's do a number like 1/2 for B. 1/2 would be a horizontal stretch by a factor of 2. So it depends on how you say it. Do you say horizontal stretch or horizontal compression? Right? right? Depending which word you use, you can say it different ways. Stretch by 1/2 is exactly the same as compress by 2. Means the same thing.
Happens if we have negative b.
If you have a negative, what does a negative cause the graph to do when you have with the stretch number? Yep, that's a flip. Okay, if b is negative, that causes a horizontal flip or reflection. Now c is multiplication like b, but c is on the outside. So what does multiplying by a number on the outside of the function do to it? Yep.
Vertical stretch.
That's a vertical stretch. And it is exactly what you would expect. If you multiply by a number like 5, that's vertical stretch by a factor of 5. If you multiply by 10, vertical stretch by 10. Now, same question Tim just asked. What if c is negative? That adds something else to it. Yep.
Vertical flip.
Yep, it's a vertical flip or a vertical reflection. You could also say reflect over the y-axis. No, vertical is reflect over the x. And what about d? That could be addition or subtraction on the outside of your function. Yeah?
Vertical shift.
That's a vertical shift, and plus would move it which way?
Up.
Up, and minus?
Down.
Down. So vertical stuff is always as you would expect it. The horizontal stuff is always reversed.
Wait, so you said d caused the vertical, and then the vertical shift.
D is a vertical shift. Yep. Adding and subtracting is always a shift. Multiplying is always a stretch. Inside the function is always a horizontal operation. Outside the function is always a vertical operation. And that's true for every single function that we ever study. All right, so let's look at this. Explain how you would sketch the square root of x minus 2 from the base case of square root of x. What would you have to do to get g of x from square root of x? Basically, take square root of x and do something. Caleb?
Shift the base equation 2 units to the right.
So if you shift the square root of x 2 units right, you would get g of x. All right, how about this one? How would you get h of x from the basic graph? We also call that the parent function. Nick?
You shift it, you horizontal shift it 3 units left.
So shift square root of x 3 units left. Yep. All right. What's kind of weird about how that's written? Think about the template that I gave you that you want to look at. You want it to be written like what's up above. What's wrong with that? Yep.
The number is equal to x.
Yeah, we don't want to write it with the number before x. So how could we rewrite that so it looks more like that?
Negative x plus 3.
Let's write it as negative x plus 3. Now, the reason I wrote A, B, C, D is because that tells you the order when you have multiple transformations. So, what would we do first on this one? Yeah.
Horizontal shift 3 units left.
So we would shift 3 units left, just like the plus 3 up there. Now, it's not a horizontal stretch because the number in front of B is really just a 1, but the negative causes what to happen? John? Well, yep, so this is a horizontal reflection. Okay, any question on that? Just describing transformations.
How would a the end affect the graph? Like if we had cube root coil and like up, like how would that affect anything? If so, how?
Like if it was a cube root?
Yeah.
Well, if it was a cube root, then, like let's say you had this, I would have you be comparing it to this. So you would just say, you would take the cube root of x and you would shift it right.
Oh, so it's the same thing.
It's the same thing. Whatever graph you're using that's been transformed, you're always going to compare it to the base case of that transformed graph. Right? You never compare a cube root to a square root.
Right.
You're always going to have the same index comparison, so there really is no difference. All right. So when we're sketching radical functions, one thing we always want to do is sketch the point that corresponds to 0, 0. And the way I refer to this point is it's either a starting point or a center point. For an even root, 0, 0 is a starting point. It starts here, and it goes in one direction. Since even roots only go in one direction, I consider that the starting point. When you have an odd root, what we're going to be doing is really finding the center point first. Odd roots go in both directions. So you're going to have a graph that looks more like this. I call that the center point. So odd roots have a center point. Even roots have a start point, and they go one way. Which way they go depends if they've been flipped or reflected. But that's kind of a standard picture for both an even root and an odd root. Okay. So, how do you find the point that corresponds to 0, 0? First, well, you have to find two values. There's an x and a y. We're going to start by finding the x value. To do that, set your radicand equal to 0. So if you had a problem like 3 plus square root of x minus 2, and I said to you, find the point that would have corresponded to 0, 0. You're basically figuring out where that point shifted to. Now you could just kind of think about it. It's been shifted right 2 up 3. So your starting point now is 2, 3. But if the transformation confuses you, the very mathematical way to do it is just set your radicand equal to 0 and solve. That's the new x value of the point that was at the origin. And then, to find the y value, just substitute 2 back in for x. 2 minus 2 is 0. Square root of 0 is 0. 0 plus 3 gives me 3. So my point is 2, 3. So that's one point we're going to get. Next, we want to include points to the left and to the right, if applicable. If it's an odd root, yes, find some more points in each direction. If it's an even root, you only want to find points that go in one direction. If you go the wrong way on an even root, you're going to get imaginary answers. And that's really all there is to sketching. So we're going to use the graphing calculator to get more points. Usually, I'd say 5 or 6 points is enough to make a good sketch. And we'll use the table. All right, so let's think about this one first. Is it going to go in one direction or both directions? Yep, both. So does that mean this graph has what we call a starting point or more of a center point?
Center.
It's got the center because it's going to go in both. So set your radicand equal to 0 and solve. That's your radicand. What does x equal in this case? 3 over 2. So the coordinates of my center point are going to be 3 over 2, comma. Now let's plug this back in. 3 over 2 is 1.5. What's 2 times 1.5? 3. What's 3 minus 3? What's the cube root of 0?
Zero.
times 2.
0.
So really, the only thing that ends up mattering, because this all comes out to 0, if you found the right number, is the plus 1. So your center point is 3/2, comma, 1. Now we need some more points in each direction. So let's type this in on y equals. Again, I don't need a graphing calculator to do this. It's just a lot faster. So 2, 3, oh, that's not going to work. 2 times 3, I have to do it like that. Because if I don't,
It would take 23.
yeah, it's going to take the 23rd root. So I have to separate that 2 off. So 2 times the cube root of 3 minus 2x plus 1. All right, and let's go to our table. We already know what should happen when I plug in 1.5. I should get 1, which I do. So we've got 1.5 comma 1. And let's get some more points. Let's do 0, 2, 5, 8, 10, -3, -6, -10. I just picked some positives, negatives, 0, and the center point. Okay, so there's my table. And do I have a graph? Nope. Okay, so let me get a graph going. Pictures. There we go. Place those. All right, and plot all these points. So 1.5, 1, 0, 3.8, 2, -1, 5, -2.8, 1, 2.8, 8, -3.7, 1, 2, 3.7, and 10, -4.1. Okay, so we got that. Now we got -3, 5.1, -6, 6 roughly, and -10, 6.6. 1, 2, 3, 4, 5, 6.6. All right, now we can pretty much see the pattern of our graph. It will continue to go up and down forever. And if you hit graph, it should have a pretty good sketch. Little gap there because it gets kind of steep. Those shouldn't be disconnected. But that's pretty much what we have. Okay. Questions on that? Now, with this one, I'm not going to go through the whole thing because I want to make sure we finish up with the last thing, which is just solving radical equations, which is only 2 examples. But with this one, the first step would be you set this equal to 0, getting x by itself. So I get x is 4/3. And is this going to be more of a center point or a starting point? It's going to be a start point, and it's only going to go in one direction. Now we got a negative in here, so that might cause a flip. So we have to think which way it might go. But it's going to end up being that is your start point. This is the key value. Can you plug in values bigger than that number, or do you have to plug in values smaller? And if you're not sure, 4/3, let's pick a number. What's a number that's easy and bigger than 4/3?
5/3.
That's not easy. No. Even easier, that I can do math in my head. 2. What's 3 times 2? Well, 6. And what's 4 minus 6? Can you take the fourth root of -2?
No.
We went the wrong way. You cannot pick numbers bigger than 4/3 when you're plotting this graph. You have to stick to numbers smaller. So try a number like 0. 3 times 0 is 0. 4 minus 0 is 4. Absolutely, you can take the fourth root of 4. So when I'm graphing this one, I would pick 4/3. Maybe I would pick 1, 0, -5, -8, -10. Those would be the ones I would probably do in the table. And I'd get my graph, and it's going to curve to the left. And that's because of this negative right here. Questions on that? That's what I wanted to, just to make sure I showed you. Stick to values that are smaller than 4/3 in this case. All right, and the last thing is solving radical equations. So the goal when you're trying to solve a radical equation is to get x by itself. But you have to get it set up correctly, which involves isolating the radical on one side of the equation and then canceling that radical out by using the power. What power? Depends on what radical. If you have a square root in the problem, you're going to use a square. If you have a cube root in the problem, you're going to use a cube. And we have to remember that we are not doing operations on individual terms. We're doing an operation to the entire side of an equation, which usually means foiling is going to be involved. Okay. I just want to see the two that I have. Here we go. That one. I'm going to do number 7 first because that's actually easier. You do have to check for extraneous solutions, okay, like we mentioned yesterday. And we're going to start with example 7. The reason why, don't write example 6 yet, is example 6 has 2 radicals. You're going to have to do squaring twice. You have to, however many radicals you have, that makes it more complicated. This has 1 radical. So we're only going to have to do something once. What do I have to do to each side here to get rid of this cube root? Yep.
You got cube each
Cube.
side.
So we're going to cube and cube. That gives me x squared minus 2x plus 2 equals x cubed. Now, whenever we have 4 terms, we either would have to graph it, or what's the type of factoring we can try if it works? Yep. Yeah, the group factoring. So what we're going to do is we're going to try putting, let's just put everything on the right. You could do it on the left, but so I'm going to have x cubed minus x squared plus 2x minus 2. So x cubed, that becomes a minus, that becomes a plus, that becomes a minus. Now, what can you factor out of the first 2 terms here? And if you do that, what's left?
Was it x plus 4 or x minus 1?
X minus 1. What can you factor out of the next 2?
2.
2. And what's left?
X minus 1.
Oh, it's beautiful. Now, what can we factor out of this and that?
X minus 1.
We can pull the x minus 1 out of each term. Someone else tell me if I pull the x minus 1 out of the first term, what's left?
X squared. Or, sorry.
Caleb?
X squared.
X squared? And what if we pull the x minus 1 out of the second term? What's left? Yep. Someone say? Yeah, go ahead. Plus 2. Now, set each one of those factors equal to 0 and solve. What happens if you try to set this equal to 0?
Try to do the square root of it.
You trying to do the square root of what number?
Negative.
-2. And what kind of number would that be?
Imaginary.
So forget about this. That has imaginary solutions. How about this one? So we set that equal to 0, solve it. And that's the answer to the problem. Let's check it and make sure it's not extraneous. What's 1 squared? 2 times 1?
2.
What's 1 minus 2? Negative 1 plus 2. What's the cube root of 1? So we got a 1 on the left. And what did we plug in? 1. What's, originally the problem was just equals, and we had an x. So let me just write it the way it was originally. That's what you had. So we got 1 on the left. And if you plug in 1 on the right, what do you get? 1. So it works. Hey, 1 equals 1. That's an easier root problem to solve because you only had 1 root. Let's finish up by looking at a 2-root problem. The first step is you need to isolate a radical on one side, meaning I need one radical all by itself. I don't have that right now. I have 2 radicals on the same side. What could I do to get one radical by itself? Yeah?
Just add a square root of 4x plus 9 to both sides.
Yep. Let's add the square root of 4x plus 9 to both sides. Now, I can get rid of this radical on the left. What would I have to do to each side to get rid of this radical on the left? Nick?
Take the square root, or
Well, if we take a square root of a square root, we're going to have a 4th root.
you square it.
We want to square it, yes. And remember, you're not doing operations on individual terms. You're doing it on the entire side. So what's on the right-hand side really means this. You have to FOIL that, okay? Left side is easy. Now, we're doing the right side, and do not FOIL, do not square the individual terms. That's not what you're doing. You're squaring the side. So, 1 times 1 gives me 1. I have 1 times the square root of 4x plus 9, and another 1 times the square root of 4x plus 9. So how many square root 4x plus 9s do I have? 2. Of the square root 4x plus 9s. And what's the square root of 4x plus 9 times the square root of 4x plus 9?
4x plus 9.
It's basically means this. You're multiplying it by itself, which means you're squaring it, so you just get 4x plus 9. Now, how many roots are left in this problem? 1. We had 2, now we have 1. A lot of like terms are going to be able to be combined here. 6x plus 12. You know what? Actually, let's do it right here. What do I have if I combine my constants? What do I have on the right? 10. So I'm going to do a minus 10 on both sides. If I do a minus 10 on the right, it cancels out the 1 and the 9. Then I also have to do it on the left. Let's also move the 4x over. How would I move that?
Subtract it.
Subtract it. That's gone. Now on the right, we don't quite have the root by itself, but we almost do. We have 2 square roots of 4x plus 9. And what do I have on the left?
2x plus
2x plus 2. Now, how can I move this 2 over to the left? Divide by 2 by 2. What's 2x plus 2 divided by 2?
2. X plus 1.
X plus 1. Now we're down to a pretty simple equation. What do you think I have to do on each side now? Square it again. Sometimes you have to do it twice. This is doing it twice. When we square what's on the right, that's easy. How about when you square what's on the left?
X squared plus 1.
X squared plus 2.
X squared plus 2x plus 1. Remember, that's a FOIL. Okay? So x squared plus 2x plus 1. Now, what kind of equation do we have? Quadratic. Easy. Just set it equal to 0, and hopefully you can factor it. If you can't, use quadratic formula. So x squared minus the 4x over, so that gives me a minus 2x, and I'm going to minus the 9, which gives me that. Let's see if we can factor. What would my signs have to be?
Plus
Plus minus. Two numbers that multiply to give me 8 and subtract to give me 2. So we have let's try a negative 4 and a 2. X squared minus 4x plus 2x. Perfect. What are my two answers for x? Negative 2 and 4. And all we have to do is make sure that they don't cause us to divide by 0. So negative 2 and 4. Or actually, we wouldn't have a divide by 0, but we have to check. All right, let's check negative 2. What's 6 times negative 2? Plus 12?
0.
And what's the square root of 0?
0.
So we have 0 minus, we're plugging in negative 2, right? What's 4 times negative 2? Negative 8 plus 9
1.
is 1. And what's the square root of 1? 1 equals 1. What's 0 minus 1?
Negative 1.
So what happened?
Didn't work.
Didn't work. So negative 2 is extraneous. All right, let's check 4. All right, what's 6 times 4? Plus 12? What's the square root of 36? 6 minus, what are we plugging in? I forgot. 4 times 4 is plus 9. What's the square root of 25? 5. What's 6 minus 5? Perfect. So, the answer here is just 4. Okay, so that's radicals. So we can practice solving a couple more in the homework, but we got through everything, graphing and solving. And that ends chapter 4. This, we can go over one if we need to in the homework. The graphing here is very simple. You put this in y1, you put this in y2, and you're calculating where one graph is above another by using an intercept. Something we've done many times. But we can definitely do one like that if we need to. So that's the homework on 255, 1356, 12 to 14, 20 to 22, and 28, 31, and 35. Right, we'll go over that tomorrow, and then don't forget on Thursday I will be here for extra help, and we'll have our test on Friday, first test for term 2.